Alright, guys, you have made it to the very last lesson of Unit 2. This is the last lesson of the last part of Unit 2. So the last topic for linear equations is going to be what we call sequences. It feels a little different, it works a little different, it's got new notation, but bear in mind as we go through this lesson and these examples that it really is just another way of talking about linear equations, which by this point you guys should be so good at that this doesn't even cause a bit of a problem. All right, let's go ahead and get to it. So for the last lesson of Unit 2C, we're going to be talking about arithmetic sequences. Our learning target for this is that I understand that sequences are a function with a domain of, we're going to change that from integers to natural numbers. Because the domain in sequences are just your counting numbers, 1, 2, 3, 4, and so on. Integers would include negatives, which sequences do not. Before we get into the notes proper, though, let's go ahead and get some definitions down. So go ahead and pause me and get these definitions copied into your glossary. All right, so you should have these three written down. I'm just going to talk about them very briefly. An arithmetic sequence is a sequence of numbers in which the difference between any two consecutive terms is the same. So what that's saying is it's just going to be a list of numbers, except the difference between each set of numbers is going to be the same amount. We talk about sequences from two different perspectives. One is the explicit formula and the other is recursive. The explicit formula allows you to directly compute any term. So if I want the 15th number in a sequence, then I can figure that out with the explicit formula. The recursive formula, however, requires the computation of all previous terms to find the value of a sub n. So what that is trying to say is if I want the 15th term there, then I have to know the first term, the second term, the third term, all the way up through the 14th term in order to get that 15th term. So let's go ahead and jump to our notes then. A sequence is an ordered list of numbers, pictures, letters, geometric figures, pretty much anything you want. In this class we are going to be focusing on numbers, but just bear in mind that the word sequence just means pattern, basically. It's the list that falls into some sort of pattern. Because we're talking about arithmetic sequences, though, we are going to be looking at numbers here. When you're talking about a sequence, each number is called a term. We usually separate them with commas. That's just so that if you have a sequence that goes 1, 2, 3, you don't think it's 123. You realize that those are three separate terms. You can also think of a sequence as a function whose domain consists of consecutive natural numbers. So although this is a linear relationship, so we expect the domain to be all real numbers, arithmetic sequences restrict it. It becomes a discrete function or a disjointed one where you're jumping from an input of 1 to an input of 2 and 3 and 4. You're only looking at those counting numbers. Now there is a new notation we have to look at called sequence notation. In sequence notation, instead of using f of x or xy notation, we use something that looks like this. Each term has a number. So the first term is a sub 1, the second term is a sub 2, the third term is a sub 3, and so on. So a sub 2 represents the second term in a sequence. Using this notation, if you see something that looks like this, a sub n, that represents the nth term. Really, guys, that just means that's the unknown term that I want to find. Another important piece of notation is when you see this a sub n minus 1, notice that the whole thing n minus 1 is a subscript. That is the previous term. So when I'm trying to find this magical nth term, n sub 1, a sub n minus 1 refers to the term right before the one I'm looking for. The subscript is called the index, and it refers to the term number. So if I'm talking about an index of 2, that's that sub 2 right there. All right, so in an arithmetic sequence, a common number, which we call the common difference, and it's also in formulas used, we use D for that common difference, is added to each term in the sequence. In order to get from one term to the next, you add this same amount. It should feel kind of like a rate of change or a slope because it is that common difference, that amount that's changing each time. For example, in this sequence, 5, 10, 15, 20, 25, we know that it's arithmetic because it has a common difference of 5. Each term, to get from the previous term to the next one, we add 5. 5 plus 5 is 10, 10 plus 5 is 15, 15 plus 5 is 20, and so on. Arithmetic sequences are linear functions. I've said that a couple times now, but it's important that you realize that it is linear because it has that common difference, which is basically a constant rate of change, which is what makes something linear. We have a couple different ways of writing those sequences, and this is that recursive and explicit formula that I talked about earlier. The first one that we're going to talk about is recursive. So remember that instead of using x and y or f of x and x, we're going to use a sub n and n. And your n kind of takes the place of your x. It's not a direct correlation, but that n replaces x, and that a sub n kind of replaces y, or f of x. Now, the formulas we're going to be using for this are on your formula sheet, and it's really important that you look at that and figure out what it looks like because they're kind of weird looking and hard to memorize. So the recursive formula for an arithmetic sequence looks like this. We have a sub n equals a sub n minus 1 plus d. Remember that a sub n is my current term, it's the term I'm looking for. A sub n minus 1 is the term right before the one I'm looking for, and d stands for that common difference. So let's do some examples with this. They want us to write a recursive formula for this sequence and then use it to find a sub 7. So this sequence, the first thing I need to identify is my common difference. So to go from 3 to 6, I'm adding 3. Just to make sure that this is arithmetic, I'm going to make sure that I'm adding 3 each time, and I am. So the recursive formula then is a sub n equals a sub n minus 1 plus, and we just found that that common difference is 3. That's all you got to do to write the recursive formula. Now, because in a recursive formula you have to know the previous term in order to find the first one, you'll also usually see it listed with an extra bit of information. They'll tell you this is the recursive formula. Also, the first term is 3. Because if I'm going to use this formula, I have to be able to have a starting point. I have to know that first term. Now, it wants us to find a sub 7. This is a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So if I'm going to go to a sub 7, then I need to say plus 3, which gives me 18, and that's a sub 6. And then the next term, I would say plus 3, that would be a sub 7, and it's 21. If I were going to use the formula, I would say a sub 7 equals a sub n minus 1 would be a sub 6 plus 3, and a sub 6 is 18. So it's 18 plus 3 is 21. Okay? Using the recursive formula is great and easy, and all you got to do is keep adding 3 if you only need the 7th term. But when it becomes a problem is when we need to find the 25th term or the 100th term or something crazy like that. I don't want to have to find 99 terms just to figure out a sub 100. So here's where we get the explicit formula. So let's go ahead and move into that. The explicit formula looks like this. We have a sub n, which is my current term or the term I'm looking for, is equal to a sub 1 plus n minus 1 times d. Now, a sub 1 is your first term. It's going to be given to you in these formulas. N is your index or the term number that you're looking for. So if I'm told to look for a sub 7, I'm plugging a 7 in right there because that's my term number. And then I also still need that common difference. In example 2, we're asked to write the explicit formula for the following sequence and then use it to find a sub 7 and a sub 20. It's the exact same sequence we looked at in example 1, but this time we're using the explicit formula. So we'll see how that's a little bit easier, or just look at the differences between the two. So since we've already looked at this sequence, we already know that the common difference is plus 3 because I'm adding 3 to get from one term to the next. With the explicit formula, it looks like this. Notice that in this little poster that we put here, the common difference is on the other side of that parentheses. Remember, guys, the commutative property says it doesn't matter what side I put it in. Either way, I'm going to be distributing it. So here, we're saying that common difference is getting distributed to the n and to the 1. Here, the same thing would happen. I would just be going from behind rather than from in front of it. So when I do this problem, my a sub n doesn't get changed. My a sub 1 gets replaced with the first term, which in this case is 3, plus I've got the common difference, which happens to be 3 as well. They won't always be the same number. And then n stays the same and minus 1 stays the same. So the things that are boxed in here are the only things you're replacing. Notice the recursive formula, the only thing that was replaced was that common difference, which is what we did in the previous example. So now I'm going to go ahead and simplify this a bit, which means I'm going to distribute that 3. So a sub n equals 3 plus 3 times n is 3n. 3 times negative 1 is negative 3. And then I can combine like terms if I want. So 3 plus negative 3 is 0. So all I have left is 3n. So I've got a sub n equals 3n. Now I can use this, it's simplified, and I can use it to find whatever term I want. If I want a sub 7, then I'm putting a sub 7 equals 3 times 7, because remember, n is your term number. So I'm just, or your index. So I'm just plugging that 7 in for my n. Just like when we did f of x and I wanted to find f of 7, I just plugged 7 in for all the x's. So my solution then, a sub 7 is 21, which is exactly what we found when we used the recursive formula, but this allowed me to do it by just plugging in one value. I can also use that same a sub n equals 3n to find the second term they asked for, which was a sub 20. Now remember, if we were using the recursive formula, I would have to find all the terms in between 7 and 20. Here, though, I get to just plug in 20, and 3 times 20 is 60. So the 20th term in this sequence, if I continued it out, would be 60. And that's basically all there is to arithmetic sequences. There is some practice. Make sure you do that and check the application box because I believe there's an application as well. Let us know if you have any questions.